Hello, welcome back to the series on quantum mechanics. To keep things light, let's start with a joke. Imagine you're driving down the highway and a police officer happens to notice that your speed is too high and decides to pull you over. And the first question she asks is, do you know how fast you were going, sir? And if you're a theoretical physicist and you want to be clever, you would say, no, ma'am, but I do know where I am. Well, any police officer worth her salt must have done a basic physics course on mechanics that would immediately tell her that you're trying to be clever because in the macroscopic world and describing macroscopic things like us or the car that you're traveling in does not really give a sense to what you're saying. So the policewoman would be quite irritated by your answer, and you might as well get a ticket. So be careful when you're trying to be clever with the law. Anyways, hidden in this joke is ingrained one of the most utterly confusing but yet unbroken laws of quantum mechanics. Let's dive into what I'm talking about. And essentially, you've guessed it, I'm talking about Heisenberg's uncertainty principle. This is due to Heisenberg, not this one, rather Werner Heisenberg, who in around 1927 had this insight about the nature of quantum particles. He said that it is not possible to measure the position and the momentum of a quantum particle simultaneously. Meaning, if you are trying to measure the position of a quantum particle, like an electron, for example, then you immediately would have to lose information about how fast it is moving. Immediately, you notice that this is quite different from classical mechanics. If you throw a ball upwards, it's a very simple mechanics problem. You can immediately determine how fast the ball is traveling given initial conditions, and also you can determine where it ends up or where it is at a given time. So this is a very confusing insight at first glance, and I will try to make this notion easy for you. And this is a direct consequence we'll see of the wave nature of quantum particles. So when I say quantum particles, remember we have discussed this. Particles like the electrons, the photons, these are all particles. They're lumpy things with definite mass. However, in the quantum world, they do behave or they exhibit certain behaviors like diffraction patterns that resemble waves. And due to that kind of behavior, we'll see that the Heisenberg uncertainty principle really has immense consequences in quantum mechanics. So let's go back to you and your friend playing with a rope. And we have discussed this in the previous lecture that on the rope between two fixed endpoints, you and your friend, you can make specific shapes. Let's consider this shape. So this is a very nice shape to look at, and this immediately looks to you as if it's a sinusoidal wave or any kind of a periodic wave. Okay, and you can, if someone asks you what is the wavelength of this wave, you can give them an answer because this is a periodic wave. The wavelength is the measure of the distance between two minimas or two maximas, and let's say the wavelength for this wave is 6 centimeters. So you can easily calculate it or measure it however you want to think about it. But if someone were to ask you, where is the wave? Well, you look at this picture and you see, okay, it's continuously going from you to your friend and maybe it bounces back to you. So at any given time, it may be anywhere. So the location of the wave is not very clear. All right. So notice that you have a very precise wavelength, 6 centimeters, but where the wave is located in space is not known or it's very unclear. Now imagine you can have a very much simpler kind of a shape or waveform if you jerk the rope once. So this is the waveform you end up with, okay? By giving the rope a single jerk. Now, if someone were to ask you what is the wavelength of this wave, you'd be pretty confused and scratching your head because wavelengths, the notion of wavelengths occur when you have maximas and minimas. However, this kind of a shape does not really give you that notion clearly. So in this case, you don't have a well-defined wavelength anymore. However, if someone asks you what is the location of the wave, clearly it is located at the bump of the wave, right? So it's very clear where the wave actually is located in space. So whenever you measure the wavelength precisely, you can't really tell the location. Whenever you measure the location very clearly, the notion of wavelengths become unclear. It's very automatic. It's very natural. There is nothing artificial going on. You can now generate numerous waveforms. They will have specific frequencies and specific wavelengths between the two of you. And let's say we generate many such waveforms. This one, or this one, or this one, or even this one, among others, right? And if you were to be asked where the resulting wave is of these series of waveforms, well, the best you can do is add them up, right? And if you add them up, you'll notice there will be some places where numerous waves can add together. We call that those locations constructive interference, where their amplitude increases. And at other places, at other locations, they will interfere destructively and their amplitudes will be minimized or cancelled. Let's look at one location, for example. Let's say along this dashed line. So along this dashed line, you see here, this is a maxima, all right? And if you added the second wave here, this looks very close to the minima, right? So if these two waves were to add up, then they would almost cancel, but they will not exactly cancel, but rather their amplitude will be diminished because one is highly positive at this location, while the other is kind of negative at this location. So they add up to give you a small amplitude. If you add the resulting to this wave, you see that this is again a maxima here. So your amplitude gets up again. And if you add it ultimately to this one, you see that this is again close to the minima. So your amplitude gets minimized again, right? So ultimately, some locations will average out to zero or very low amplitude, while other locations will be maximized, all right? And you may end up with a wave that looks somewhat like that, all right? Now, what do you think about this wave? Well, if you take a close look at it, it looks like you can kind of answer the question where the wave is located in space because the waveform is not too big in its entirety, right? So we can say that this wave is somewhat clearly localized. However, we have again traded off something else. Now, the notion of wavelength is no longer that precise, right? Because you have a waveform that it is kind of somewhere between here and here. So this is a if this is a small region in space, we can call this okay. This is the location of the waveform. However, this is not a periodic wave anymore, and hence you have lost the notion of a wavelength again. Now, in quantum mechanics, we have briefly introduced the de Broglie equation that relates the wavelength to the momentum of the particle. You basically take the wave property of a wavelength and you relate it to the momentum, which is a particle like property, and you get the de Broglie equation. So in quantum mechanics, we have the de Broglie equation, which is lambda equals h over p, where h is the Planck constant and p is the momentum of the said particle, right? And you immediately notice that by localizing this wave, you have lost the preciseness of the wavelength. The wavelength is now unclear. If the wavelength is now unclear, that means your momentum is also now unclear. Or, in other words, the wavelength is imprecise, which results in an uncertainty in the momentum of the wave. Mathematically, the uncertainty principle is stated as follows: the product of the uncertainty in position, which is delta x, with the uncertainty in momentum, which is delta p, And this product will always be greater than or equal to h bar over 2, where h bar is the reduced Planck constant, and this is h over 2 pi. So this is the mathematical relationship, and this tells me that if you have a very precise location, then your momentum becomes very imprecise. And if you have a very precise momentum, then you are no longer clear about where the location of the particle. In our case, this particle or wave, we can use interchangeably because we know that particles are particles, but they exhibit wave-like behavior, and we choose the wave nature of particles to describe quantum particles. So for any quantum particle described by a wave, the more localized the particle is, the more spread out its momentum becomes. However, there's a catch to all of this, and that catch is unique to quantum mechanics. So no matter how precisely you determine the location of the electron, you can see it's clearly still defined by this waveform. And a waveform by nature is a spread in space, right? So it is, if someone asks you where will you find the particle, it may be found here, may be found here, may be found here, may be found here, or wherever within this waveform, right? So this particle is still described by kind of a spread out distribution. So if you were to ask me where the location of the particle is, the best I can do is really estimate a location within this spread out distribution. And therefore, we say in quantum mechanics, the location of the particle is described by a property of the waveform, which is known as the wave function, which is usually denoted by the Greek letter psi. And psi is a function of position and time, meaning it can change with time and it is spread out in space. Okay? So, with this notion, whenever we make measurements and if we want to predict the results of that measurement, the best we can really do is estimate a probability for where we can see or find the particle after measurement. And that probability is given by the absolute value of psi squared. And we'll talk more about this as we go in more depth in the course. So, we have seen the uncertainty principle, we have seen the quantum nature, the probabilistic nature of the quantum world, and now we'll end this video with a brief discussion of the profound consequences of the combination of Heisenberg uncertainty principle and the probabilistic nature of quantum particles. And this starts by discussing one of the most important consequences of the Heisenberg uncertainty principle in correcting Niels Bohr's atomic model, which was proposed in 1913. So, this is right after the birth of quantum mechanics, and Niels Bohr proposed and won a Nobel Prize consequently for his atomic structure model, where he imagined that the atoms are kind of like the planets, right? So, sun at the center, the planets orbiting the sun. Here, he said, okay, the nucleus, highly dense thing, is at the middle, and the electrons can orbit the nucleus at fixed energy levels. However, there is a problem with it. The problem is the electron orbiting this nucleus is a charged particle. And an orbit means that the electron is kind of orbiting or circling the nucleus, if you were. And if it did, electron being a charged particle, as it orbits, it is accelerating because the electron is changing direction at every point. And if it does accelerate, a charged particle will lose energy. If it lost energy, then the notion of fixed orbits become kind of fuzzy because the more energy it loses, the more closer to the nucleus the orbit comes, and there is a chance that the electron will ultimately crash into the nucleus and result in kind of no stable atoms. No stable atoms therefore means no us, no quantum mechanics, no quantum field theory, and basically no life as we know it. Heisenberg, or Heisenberg's uncertainty principle, forbids this kind of a chance of an instability like this. How? Well, if the energy lost by the electron as it orbited the nucleus would result in enclosing the nucleus in closer orbits, that is closer to the electron is coming nearer and nearer every time it circles the nucleus. That means if you were to take a snapshot of the electron's motion, you would be very precise in measuring the location of the electron, whether it's here or there, wherever. But also, since you know the electron is losing energy, you're indirectly also measuring a precise value for the energy. A precise value for the energy means a precise value for the momentum of the electron. But that is not possible. You cannot have a measurement where you're measuring the position and the momentum precisely together. Essentially, what that means is that the closer the electron comes to the nucleus, the higher the uncertainty in momentum becomes. That means the greater its speed is. And the higher in uncertainty in momentum means that rather than coming inwards, the electron will be pushed outwards due to this very high momentum, right? So that means we are saved from the instability that was inbuilt in Niels Bohr's model without the uncertainty principle. As a result, we have now really jotted down a more concrete and correct model of the atomic structure, which abides by the laws of quantum mechanics dictated by Heisenberg's uncertainty principle. And that is the notion of an electron cloud surrounding the nucleus. So essentially, there's a cloud in which the electron can reside, and it can be close to the nucleus, but there's a limit to how close it can be. It can be far away from the nucleus, and again, the farther you are from the nucleus, the less the probability becomes of finding the electrons. And this electron cloud is nothing but a probability density that is derived from the wave function of the electron. All right. So I hope the idea of this video is clear. If anything's unclear, make sure that you're commenting below the video to let me know or ask me any questions. I'll see you in the next one. Thank you.